And we go next to Sugi Dorfman to lead the next session.
Thanks, Don, and thanks, Renata. I'm going to shift us to the lower mantle. Well, Renata also took us through this realm as well. But our first talk of this session on Earth's deep interior is going to be from Guillaume Morard. Thank you for sharing your screen, Guillaume, on structural and electronic transitions in liquid FeO. Guillaume, I'm going to let you take it away right away.
Thanks a lot. Yeah, thanks a lot, Suki. So, and thanks a lot for the organizer for giving me opportunity to present this work. So today I will shift in this one. So I wanted to present this work I performed during the, partially when I was at the base at the IMPMC in Paris, and now I'm in, and now I'm moved to Grenoble since 2 years, continuing on this work. This work was partially funded by 2 ERC grants here. And so the idea was today to present only one work on the FeO and why FeO. I think so yes, first of all, I wanted to also, this work is not only done by myself. Of course, there is experimental part that is done by with the help of people in APS, in Argonne National Lab on the JC Cars beamline. So Aaron Greenberg, Stella Sheraton with other collaborators. Partially also done at the ESRF on the high pressure beamline. And also want to acknowledge the part, we also mixed some ab initio calculation performed by Johan Boucher from the CEA and some thermodynamic calculation was quite useful to interpret our data by Tilly Rivaldi. So this present work is submitted to EPSL. So I think I don't need to convince you that FeO is important, because what is really nice when you study FeO is that it's an end member for planetary science, but it's also pertinent for deep mantles, so pertinent for MgFeO and for Periclase as an end member, but also for the core. And that's what is nice. It's you study FeO, you can study part of the core and part of the mantle at the same time, because and you have very interesting features going on in the binary FeO, and as well as you have features going on in the mantle correlated with FeO. So first of all, the first question I wanted to address. Sorry, I don't know how to move that. Yes, so the first question I wanted to address was to discuss the effect of the metal to insulator transition in the B1 structure of FeO. So this this transition has been noticed by different ways. So by conductivity. So Ota and co-authors have seen this jump in the conductivity inferred, showing this transition from an insulating behavior to a metallic behavior at high temperature in the FeO, in the solid FeO. And also it has been some signature on the emissivity of the structure at the same condition. So in the same year it came out, these 2 papers. And the question is, what is the effect on this transition on the properties? So in fact, it has been shown from this work, there is a very small chain. You've seen that there is a very small chain of the volume from the B1 structure. But in fact, when you go, it's a bit different, but for the spin quasar, for example, in the B8, in FeO, there is a large volume change. So we wanted to see if we can track volume change in the B1 structure related with this different spin or insulator to metal transition. And so we wanted to infer that. So we did this fitting of the volume we had. We used, so by diffraction, in situ X-ray diffraction, laser heating experiments. We have all this data set for volume of the B1 structure and fitting equation of states. And we were able to use also complement our data set with the previous data set that was at higher pressure by Rebecca Fisher. And so we fit all of that, trying to infer an equation of state. And so what we obtain is the following. When we look at the volume of the B1 FEO around an isotherm of 2000 Kelvin. And if you look at here, so from 60 GPa and 2000 K roughly, where we expect to have the insulator to metal, we do not see any volume change in the B1. So there is no volume discontinuity that could be resolved here for the in the B1 FEO. And in addition, we as well, at the beginning wanted to study melting, but going to the melt, we were able to study the solid, and we were able to track like that the melting curve. We extend a bit the pressure range for the melting curve of FEO in good agreement with previous work. And you see here, this is a two metal insulator to metal transition in the B1 structure, and we do not see any kink or any signature of this transition on the FEO melting curve. So that's why it's quite interesting is to see that on this FEO melting curve, there is no sign of any effect of this transition. So as it has been addressed before, the question of this workshop is also to discuss a bit the future scientific problem to be addressed and technical advances. So for each question I will address here, I will try to discuss that. And this is related with discussion we had before regarding the metrology. Metrology is not the most, I will say, appealing part of mineral physics. Yeah, so we want to discover new phases and so on, but basically metrology is the metrology is at the heart of our work. And I just present two work here that I've been collaborating with, participating on. So is to on equation of state. And I think one of the end goal with the metrology is to in order to increase the accuracy on the thermal equation of state and to have better agreements. So here this is typically, and one of the things we've done, for example, in this work from Eric and Moon on iron silicon alloy, was to do isothermal compression. So compressing along an isotherm and keeping for membrane driven DAC. And so this could be in the future very interesting to do that also potentially in DDAC at high temperature in dynamic DAC. So you compress and do laser heating, and you will have a lot of data points on an isotherm. Also, one point is the fast acquisition could be quite interesting for the high temperature when you're getting close to the melting line, because you have a large grain growth or contamination, and to have millisecond acquisition could be very interesting to have accurate volume at these very high temperatures that are usually neglected in the equation state or usually removed because the grains are too big. It's very difficult to get accurate volume on that point. Potentially I was putting temperature regulation because it could be very nice if you do this kind of isothermal compression to be able to regulate the temperature, the laser heating and the laser power in situ. If you have large data set for this type of equation of state, having automated large data set analysis for the fitting and to have all the data analyzed at the same time with the same parameter. As I say, the metrology, where do you take the calibrants? That's a very important question. Usually in the experiment I show here, we use the KC, the pressure medium, to measure the sample pressure, and maybe having something mixed with the sample that do not react could help, and to have a better the same temperature for both sample and calibrant. And finally, having better constraint on the temperature gradient is something that we're working on Grenoble to do finite element modeling to constrain the temperature gradients in our experiments. So the second question now is that we saw that this insulator to metal transition doesn't seem to have any effect on the B1 structure. What is the effect on the liquid part, the surrounding liquid? So we did this experiment on the two setups. So one is on the JC cards using the multi-channel collimator called Solar slits, and the other one without any multi-channel collimator on the high pressure beamline ID27. So the two different setup on a similar sample. It was FEO. I didn't put the number here. It's 0.96, I think. It was a single crystal given by Steve Jacobsen, synthesized in oven. We also work on the powder. So you have here the two. This is a cross section of the sample with FIB with the two domain of liquid here. So this is the type of data we got on JC cars. What I would like to point out that is very important with SOLSAT is the correction from the absorption of the downstream mirror. You need to have a good to have a transfer function, because here you have the mirror that is bringing the laser and the imaging that is absorbing a part of the sample in white, and in red you have the after correction, and you see that it's quite nice and straight line for the liquid. So you need to remove also the background. This is the background you take on the KCl on the side of the sample, and this is a type of image that we obtain. I just want to point out here something on the development that could be quite nice in the future, is that you see you need to mask a lot of part on the image, and on that means that you will have a lot of noise at the end, and sometimes you even have parts that you don't have you have nothing on this part, for example. And this is quite important, I think, to the enlargement of the serial slit, to have a larger angle accessible and to have a larger part of the ring of the liquid, to have better signal to noise ratio with these slits. Because that's something that when you don't use serial slits, for example, here, you see you have a large background of the diamond, but you have lower Q range, because after you don't have, it's very difficult to get a signal to noise ratio when you go above 7 angstrom, but the background is quite smooth. So you see both techniques are complementary. They have both advantages or disadvantages, but they can give both good results. For the analysis, I use part of the software that is actually, this is a paper by Silvia Boccato and people from IMPMC. We developed a software for the analysis of liquid called Amorpheus. And one part of the software is this RPS, this remove peaks and smooth. So it removes the KCl peaks, all the diffraction peaks. You can click and say to remove the peaks, and it interpolate below these peaks, the signal. And there's also a smoothing function in order to remove this, to smooth the data. So, and after you do the Fourier transform to get the G of R. And so this is the type of data we obtain. So this is data in black. Of course, it's not our data. It's too beautiful. This is from ambient pressure. And by increasing the pressure here, you have the change. You see here some change in the structure factor that you have here with the appearance of this bump here. And on the G of R, you have the change with the evolution of this bump that changed to the left. So I will try to, in order to try to assign what are these features that we see in the liquid to bond distance and so on, we collaborate with Johan Boucher from the CA that I named before to do some ab initio molecular dynamics, and to perform with ab init package. So thanks to Renata Jankovic talk before, you have a good, now you know everything about ab initio. And so we use the GGA plus U, and you see that this plus U is what people are using a lot for in iron oxygen, to try to model iron oxygen, and to the devil is hiding in this plus U. I won't enter in the detail here, but it's quite tricky to make this kind of simulation. And here you have the partial structure factor of the liquid FeO. And so we can assign now the first bump here to FeO distance, the second one here to FeFe, and then basically FeO is not appearing. So we took our experimental data, and using a physics software, we fit both a contribution with 2 Gaussian and the rest of the signal with a sigmoid. And the Fiat process, as I say, was done using physics software. What is quite nice here, you can see the excellent agreement, at least from the shape, between the experimental data and we've done 2 types of ab initio calculation. One is magnetic. So magnetic, we make the Fe atom, Johan put the Fe atoms in a high spin state, And a non-magnetic, where the magnetic moment was forced to zero in a non-spin polarized moment. So basically, the magnetic is the high spin, and the non-magnetic would be called close to the low spin state. And you see, you have a strong difference in the structure between the two type of simulation. So we can compare now this, we'll show the comparison with ab initio, but we could also compare with liquid iron. And this is liquid iron data we obtained so published last year in PRL with the collaboration with the group of Kei Rose in Japan, in Tokyo, in Todai. Just to check here, you see the evolution, the compression of the first sphere of the FeFe, and we can here follow also the FeFe bond in liquid FeO and compare. And so what is very interesting is this is the result we obtained. So you have the ab initio. So you see here the low pressure, we have the FeFe is close to the magnetic one, and the non-magnetic is very similar to the FeFe. And around 40 GPa, you have both structures that start to be compatible. You have quite similar, not the same. Of course, still a bit of, within the RY, it's quite compatible between the FeO and Fe. And what happened at 40 GPa in this in the liquid state in between these two? In fact, at around 40 GPa, you have the closure of the Fe-FeO miscibility gap. At low pressure, you have this large miscibility gap. With the Fe liquid on the left here is not compatible with the FeO liquid. And when you look at the structure, you can understand that the two structures are very different, so are not compatible. And with increasing pressure, this miscibility gap tends to shrink. And at higher pressure, seems around 44 GPa, but this is still need to be well defined. You may have a closure of the miscibility gap. We can explain with a microscopic behavior the evolution of the FeFe distance in the liquid state, the closure of the miscibility gap. So the study of liquid immiscibility in diamond nanometer, as I said, it still has to be proven, or the liquid structure at extreme pressure temperature in diamond nanometer is quite complicated. And it's one point I want to point out here that is very important, is that laser heating implies strong temperature gradients. And basically, when you do a laser heating, when you melt, the starting composition is not the same. Composition you have when you probe with X-ray is not the same as the starting composition due to chemical migration. You have a lot of recrystallization that you, for example, you see here with the FeO grain moving on the side, Fe grain staying here. So you have a lot of chemical migration, potentially carbon contamination. That's another issue. And so this is the thing that in the future people have to fight when we study melting and partial melting in diamond cell. And so I just developed a few points like that, but it's just so the idea of large volume assemblage for the large volume press to study this liquid where you have less temperature gradient is very important, in my opinion, to continue to increase the pressure in the large volume press. And as Jan Bin has shown this very interesting data on liquid MgSiO3. This is typically the kind of thing that should be pushed in to study the liquid, but also to go higher in pressure, to have new heating geometry in LHDAC to lower the temperature gradient. I just pointed out the dynamic compression because something also we've been working with, and it's quite good. You don't have chemical migration, you don't have the time of the chemical migration during dynamic compression, so it's kind of interesting too. And to study thermal expansion or liquidus temperature, that are the two things that I think where there is still a lack even for lower pressure. And I just want to advertise the experiment, and Vitaly is part of it. And so this fast heating and melting in laser heating DAC that it's planned in 2 months at the European XFEL, where we will be able at the microseconds to launch a pulse of YAG heating and to study with pulses of X-ray how the sample evolve in a diamond of your cell while we have this pulse of heating. So this is very interesting experiment that we will perform in 2 months in Hamburg in the European XFEL. So the third question is how this is related with the liquid spin state. also, and what means what is going on at higher pressure. Because at higher pressure, as I said before, you have this spin transition, where in the solid state here, that has been seen at around 120 GPa, where you have this volume drop, and that could be maybe still present at high temperature. A very recent paper by Eran Greenberg with also Professor Leonov for the ab initio calculation, did this work on the B1 on the FEO structure, and they were saying that maybe you have this high spins in the metallic state, a high spin B1, and that could expand up to 150 GPa, and this is supported by experiments and ab initio calculation. So how it compare with our liquid data, and that for that we did Tilio Rivaldini in Belgium did this thermodynamic calculations. So the idea is quite simple. We have the melting curve, we have the equation of state of the solid. So as on the melting curve you have the Gibbs energy of both are equal. You can try with some Helmholtz free energy approximation, and the formalism used for iron by derivative plates, you can extract the equation of state of liquid FeO around the melting curve. And so he did that, and it's very interesting when you compare this data with the density from the two ab initio calculations, so magnetic, so in high spin and low spin, I would say, and compare with other, this is the other dotted lines are previous model in the literature for the thermodynamic equation of state of the liquid. And what we can see is that our equation of state, you see that you have the transition start to, seems to start around 60 GPa in this pressure range, or 40, 60, the same pressure range when we have this, this shrink of the Fe bond distance. And it could be completed around 150 GPa, and you have this whole part in the liquid state that is in this intermediate spin, so changing the spin state in this pressure range. And so when you compare with this completely independent work by Eran, even if it's co-author on our paper, but completely independent, you see that it corresponds pretty well with this field of the high spin metallic B1 state here. So future and advance. So I think you are. I won't convince you that the spin state of iron in silicate, more generally speaking, has strong implication for density and iron partitioning and between solid and liquid, and that it's very important to determine the spin state. Also, it's a key parameter, as Renata just discussed before, to perform ab initio calculation. You need to have that input. It's very difficult to extract the spin state from the ab initio. It's good if you can have some experimental input for the ab initio calculation. And so I just want to advertise that this kind of experiment that we've been performing, so with Dan Shim and a large group, Alessandra Avadio in France also, Wendy Mao will speak just after her, Ariana Gleason, and I forget all the other people. Sorry for that, but Dan, I have to finish to read the paper, by the way, for tomorrow. So we did a combination of X-ray diffraction, free electron laser, so shock compression, and X-ray emission spectroscopy to get that. And so this is, I think, very interesting when we're speaking about combination of diagnostic. This is a good example. It's done on DFEL, but potentially in the future, maybe this kind of thing could be done also in Sumatra. So I would like to, I'm just right on time. Thanks, Stella. And so just to wrap up, we didn't see no visible effect of the insulator to metal transition in the solid B1. We have this Fe bond length shortening and could be linked with the shrinking of the miscibility gap, and potentially this evolution of the intermediate spin in this 60 to 150 GPa pressure range. So thanks a lot for your attention.
Thank you, Guillaume. Let's go ahead and take a question from Afu.
Yes, thank you so much. So FeO starting sample can be quite highly non-stoichiometric. So some samples can actually contain quite a lot of ferric ion. So I wonder how does that actually affect the experimental data in terms of the insulator metal transition, the melting curve, etc.
Yeah, sorry, as you say for the, so just to answer to your first question regarding the FEO, the non-stoichiometry. So it was 0.96, and this one was synthesized in high temperature furnace by Steve Jacobson. So it was well characterized before. And we also work with FEO powder, and we didn't see much difference regarding the liquid structure and the melting curve. And sorry for the second question.
So how does that then compare to like previous studies, right? So I know people just take FEO, like in this case, here is like FE, 0.96, which is actually good, right? But some commercial products of FEO can be like just 0.88, for example.
Yeah, I don't know. I compare with the data from Rebecca, and Rebecca data are from it's 0.94. So, and we are quite in good agreement, at least for the volume. We use the volume at high pressure, and we are quite close. So, and the melting curve is very similar. So, I don't see many difference with previous work, at least on this part, on the equation of state and on the melting curve.
Thank you.
Yen Bin?
Yes. Hi, Guillaume. Really nice work. This is really a very important experimental results. I have a question about the liquid data. I was struck by how low the oxygen contribute to the scattering in your data. Do you have any comments on that? Does that mean that the actual oxygen atoms are totally disordered? They're like
I don't know. I use the. In fact, this is the partial G of R from the ab initio, and I weight them using the Vazeda method. Comparing with the Z. So it's just the oxygen are multiplied by the ponderate by the atomic weight, basically. So that's why it's quite low. But I think also it's quite dispersed. Yes, I think also there is not much clustering of it in the liquid. I think so. I don't know. Maybe I hope I didn't do a mistake when I multiplied by the.
If you have some snapshots on the simulation, I would love to see it. I try to understand how these oxygens are distributed in the structure. It's very interesting.
I think we also show this kind of thing in. We have another paper where Johan did some calculation on the FEO liquid. It was in CRAS, Compte Rendu Académie des Sciences, the French journal that nobody reads, but and he shows snapshot of the. We have also the oxygen contribution, and we have I've been showing calculation at 5 GPa and other at 300 GPa. So we can compare like that the pressure effect on this.
Okay.
But if you want, I can send you the data.
Yes, please. Yeah, thank you very much. Yeah, nice work. Thanks.
Thanks.
Thanks again, Guillaume, for a great talk.